Welcome, everyone. Today I'm going to present on Cloudflare's serverless deployment of Osquery and how we explore big data sets. My name is Bedoya. I'm a security engineer at Cloudflare on the infrastructure and security team. We focus security challenges on the hardware, firmware, and Linux layers. And we're also a build-focused team as well and create services where necessary. What is Cloudflare? It's a globally distributed Anycast network. It's in 200 cities in more than 90 countries. There's 26 million internet properties, and 10% of Fortune 1000 customers are paying. The larger the network, the better performance and security we can deliver to our customers. CloudFlare Mission is to help build a faster and more secure internet. We cache content around the world in hundreds of data centers, and we determine the fastest delivery. We provide unlimited distributed denial of service mitigation capabilities as well. Our engineers are implementing the latest web optimization techniques, for example, TLS 1.3, with 0 round-trip time, HTTP2 plus quick, and a serverless platform called Workers. And Cloudflare also provides the fastest public DNS resolver. With so many services running in all these data centers, Cloudflare has a large attack surface. How can we gain visibility of malicious network activity to monitor bad actors? And how would we properly triage and respond to these security events? In other words, the team needed to know what's happening on the edge data centers. We needed a standardized way to collect information and analyze that information in an isolated environment. Osquery solves these concerns. Osquery was originally developed by Facebook a few years ago to monitor their infrastructure. It's now a Linux Foundation open source project with hundreds of contributors and thousands of commits, making it one of the most successful security-focused projects on GitHub. Specifically, it exposes an operating system as a high-performance database, and its design allows one to write SQL-based queries to explore an operating system efficiently and easily. In effect, it abstracts concepts such as running processes, kernel modules, sockets through these queries. And by using scheduled queries, you can create an infrastructure baseline and use that to detect anything anomalous. Osquery, to scale Osquery, there's a couple phases. One of them being endpoint configuration and inspection. Cloudflare engineers leverage Saltstack, which is built on Python to create event-driven automation to deploy code. In other words, when a data center is created, Saltstack is actually what configures the BIOS, the firmware, the encrypted file systems, and deploys the running services in what is called a high state. There's thousands of states that are executed. In other words, Saltstack powers CloudFlare. And so we needed to create our own Osquery high state. Further, Adobe has released an Osquery compliance framework for Saltstack managed servers called Stack. I recommend looking at that project. This is an Osquery salt state, and this is what orchestrates the installation of Osquery on the edge servers. On the left side, we have state information. Line 26, you can see that a package is being installed. You can define how the service runs. You define files that are necessary for its configuration. You can see that YAML is also serialized to JSON, which is what Osquery requires. You can see that we also installed extensions on line 50. This is a Prometheus metrics exporter, and then we also configure extensions. On the right side, you have pillar data, which is YAML, easy to read. And both of these screenshots it's just YAML and Python. So if you want to configure an orchestration, you would do that through Python and YAML. And these high states get executed every 15 to 30 to 45 minutes. And this deploys code to the edge. Saltstack is Cloudflare's most popular project, and there's I think on average, there's about 100 commits per day, meaning we have to ensure we need to be confident, and we need to ensure stability in these high states. So in the top, you see a Team City build, which installs a Cloudflare-specific variant of Osquery. Below is a build of the Go Prometheus metrics exporter, which monitors the health of the daemon. And what we have captured below is operational checks that happen on Salt. And because it deploys code frequently, we need to ensure that the services pass tests. Phase 2 of scaling Osquery is really on data transport and storage. We previously talked about the configuration, endpoint configuration, the inspections such as the Prometheus and extensions, but the most important parts are actually how you handle this data. To achieve this, we created Cenote. A Cenote is it's a sinkhole that uncovers groundwater underneath, and the Mayans believed it to be a portal to another cosmos. Cenote is a GCP-based serverless Osquery backend API developed in Go. Its serverless nature means it auto-scales, meaning that when Cloudflare expands its Anycast network, we automatically deploy Osquery, and any data that is received, Cenote then auto-scales. It means we don't manage servers. And this is great because as security engineers, we can just focus on the actual events. On the left, you see the Osquery logo. That represents Cloudflare's network, which then sends telemetry to Cenote in a TLS 1.3 connection to a Cloud function, which performs some business logic. It communicates with Redis. It also sends messages to a topic. And this topic allows multiple subscribers. And so we have a couple subscribers that are specifically focused on detection. One of those is Cenote detection. Another is StackDriver, which is real-time log management. The third is BigQuery, which allows analysis of data. And the fourth integration is CloudFlare SIM. And I just want to mention that Osquery is a single element of how we protect our edge servers. There's other strategies such as secure boot in practice. The published subscription model of Cenote means we can provide many-to-many asynchronous messages, and that decouples the senders and the receivers, and it creates high availability communication between these independent applications or microservices. Cenote specifically leverages Google's BigQuery for both detection and performance queries. We also have cold storage. We use Memcache. We use Google Functions. And then we push this data to a SIM as well. And you can also talk to third-party APIs if necessary. One of the advantages of serverless is its performance characteristics. And so here we've defined a test case with 500, 1,000, 5,000, and 10,000 concurrent connections to the Osquery log API. On the left, you can see the number of invocations per second of these cloud functions. And on the right, you can see the number of active instances. When 10,000 connections were made, Cenote invoked about 250 functions of the log function. And then what you see on the right is that Google will invoke these functions, but they will remain active. And so a serverless function has a concept of cold start. And initially, it sets up networking, it sets up the runtime, and then it also caches global objects. And what it shows is that about 100 to 150 active instances is plenty compute power for 500 or even 10,000 connections. What this also means is that you can make sure that your business logic is well defined to perform a function very well and efficiently. What I've captured here is a pro and a con of serverless design. What I've captured here is actually a memory leak in a Google function, because I forgot to close a Redis connection. But what's great is that even when this error condition occurs, the serverless platform just immediately invoked another function. And then by using PubSub, you actually have high availability and integrity or insurance that a message is actually received. So even when this error condition was met, like everything operated fine. What we also see here is buggy code and then code that was fixed. And so initially, it would just continually, the memory usage would just continually increase. And then after that was fixed, the memory profile of that function was around 50 or so megabytes. One of the cons or one of the considerations that you have to take are Google constraints. And functions have their own limitations. StackDriver has their own limitations. And we encountered this particular RPC error message when we were writing over 1,000 messages per minute. And what that means is that you just have to come up with creative ways to solve these problems. So things to be aware of. One of the constraints of a Google function is that you could only actually run for 5 minutes. And so you want to make sure your business logic is, again, well-defined. And there's tricks to optimizing network connections and whatnot. Another subscriber of this data is StackDriver. StackDriver is Google's observability tool. It allows you to monitor your infrastructure and improve its performance and improve application performance. In other words, it actually collects signals from running GPC services and then creates graphs, or then pushes them to this real-time log management. This can be used for manual investigation. Here you can see a node valid, enrollment of node valid, and I've redacted some sensitive information. You can see an Osquery status message. You can see an Osquery result message. And because StackDriver understands JSON, it's very friendly in the browser, and you can just open up specific arrays if you want it. Another subscriber of the Osquery data is BigQuery. BigQuery is this serverless, scalable data warehouse that allows you to make informed decisions, and it surfaces meaning to large data sets quickly. There's client libraries in Go, Python, R. What we have here is Go code that sets up a context, sets up a BigQuery client, creates a query, and then runs the context. This is great for both interactive and automated analysis. I think so far we have terabytes of data, and the queries are generally pretty quickly. Here we actually have a real data point when we were retrieving Osquery performance data of a pack, and it processed 43 gigabytes in 1.4 seconds. It's very efficient. And it also creates detection and response flows. What we have here is taking that client library and then creating a rule engine out of it. And so here is a JSON object. It has a defined structure. This runs every 30 minutes. There's a severity associated with it. And there's a query that grabs crontab-related telemetry that was collected on the edge network. There's also a playbook URL, and if this query was to return data, it would actually trigger alert ID 2002. The third phase of scaling Osquery is the visualization aspects. We mentioned automated analysis using Google functions. We mentioned manual analysis using StackDriver, and we mentioned automated analysis with BigQuery. The fourth aspect is just visualizing the data. BigQuery, in addition to running queries, also allows you to export data. And that creates data sets. So that data set can be a week, a day, or a month. And based on this static data set, you can then create graphs. And in this case, one of our team members surfaced some of the collected Osquery telemetry. I've redacted all of it, but you can see there's a section for kernel versions. If a thumb drive were used in a data center, that would get logged. And again, this is all information that was collected by Osquery on the Anycast network, sent via TLS to Cenote, and then ultimately exported. The Cenote platform is designed for data analysis and transport. We can extend the platform to address specific security challenges. We are going to add file carving support. This would allow us to retrieve a file from a metal, and then we could potentially push it off to Joe Sandbox for live malware analysis. We could also push it to a container for manual analysis. We're also looking into identifying vulnerable components in libraries. It's common for servers to be misconfigured, and so you would want to ensure that everything running is what you believe it to be. We're also interested in simulating a metal and for example, trying out a Docker escape technique or a Kubernetes escape technique to ensure that the Osquery is collecting relevant telemetry. Adversarial simulation for Linux, we're looking into that. And we're also working with industry experts to help us with vulnerability detection through an Osquery extension. And this is some of the identified engineering work that we have planned, that we're considering. Questions? Nothing.
Do you do any work to verify that the query results coming out of Osquery are cryptographically signed or anything on the way to the server, or do you just trust that they're coming in good?
So the messages are coming through TLS. But besides, no. But I think there's definitely ways to extend Osquery to support like signed queries. Any additional questions?
So you mentioned VirusTotal. I'm not super familiar with it, but would the idea be that if a user upload a file, you're using Cenote to do an external virus scan?
Potentially. The idea with the file carving support is that we can create a query to grab a file from a metal server. We would then retrieve it, and from the Cenote platform, we could perform an automated analysis by a third party, such as VirusTotal or Joe Sandbox, but we could also just do manual analysis in a container. We can retrieve the file, put it in the container, and then do an isolated analysis there.
So do you have a roadmap for patching it based on what you discovered at scale in terms of what you're operating?
I think those are, I'm not sure if I see the connection with Osquery and Cenote on that, but maybe we can talk further.
If there are no more questions. questions. Thank you very much.